Oh, okay.
All right, ready? I'm moving on. Tell me the significance of the, I'll go here in a second. What does the dummy tell you? The dummy gives us several pieces of information. What have they been so far?
The variable in the integrand.
The variable in the integrand. What else does it tell you?
The variable. It's dumb. It's just the axis. It's called a dumb.
The axis, elaborate, Arjun.
The
Perspective. Okay, so the dummy has to match the integrand. It has to match the limits. It's actually called dummy variable. I know you're probably wondering why is she calling it that. It's the dummy variable. So the dummy variable gives you information about the variable in which you're working and also the perspective. Here's the last piece of the dummy variable. This is probably the most critical piece. It's also the piece that is most abstract in nature. Okay, this is a what? Ooh, my goodness.
Riemann sum.
It's a Riemann sum. It's a limit of a Riemann sum. And when we took a limit of a Riemann sum, we remembered that, look at my notation here. I know that we call delta x just b minus a over n. This is the function evaluated at the right endpoint of each subinterval. That was a mouthful. But in terms of the rectangle, this was the rectangle's what?
Length. Width, height, length.
It's one of them. It's height.
Oh, that.
It's the rectangle's height.
Of course.
This is the rectangle's
Wait, Miss Sam.
yes.
Should I do the left one?
What?
Is it left
K.
one or
Yeah,
left?
oops, you're right. K delta x. Sorry. Let's leave it as K. Okay. That's the height and the width. Here is where you have to. This is the part about the dummy that needs to be. This is the least concrete. It's the most helpful moving forward. We know that this is equal to the definite integral from a to b of f of x dx. Let me tell you what the corresponding height and widths are. So here's the kind of conversation people have. When you're looking at this question, let me draw this here for a second. Okay, you don't have to copy this picture down necessarily, but as n approaches infinity, essentially your rectangles get narrower and narrower and narrower. Delta x approaches 0. Essentially, your rectangles squeeze to become what? Lines. Like, we have to be careful. We're talking just very metaphorically. Essentially, your rectangles become lines. And so, what you could think of is this area is essentially, yes, the area of all these rectangles added up. But as delta x approaches 0, essentially what you're adding up are, again, listen to this phrase, areas of lines, like this line's area plus this line's area plus this line's area, so to speak. Like, as an analogy, if you look at this, do you see height? This here is height. This delta x dx actually is width. Dx literally by definition means, delta x infinitesimally small. So if you look at the integrand, including the dummy, I hope you see shadows of height times width. Dx literally means, the definition for dx equals delta x as it approaches 0. Dx is equal to a really small delta x. So I hope you see a little bit of this dummy is just kind of the evolution of the width as it approaches 0. This here, I have to put air quotes, it's height, but in the sense that height is like the height of this infinitesimally small rectangle. Okay, that is the last piece of the dummy that you need for us to go to the next step. Any questions on those ideas so far yet? Jason?
If we do use up, what's the still?
So when you do U sub, it still is going to be the width, but it gets a little bit congested because then it's F of U, that's the new height. That's a good question. I'll go there soon, Jason. Like I'll go there very, very soon. Now this piece of paper, it is blank because holy moly, there's gonna be a lot we're gonna write on this. Please take that all the way through. Take it all the way through, go pass it back, pass it back, pass it back. Okay? Going into this very deliberately. All right?
Miss Ham, should I just like draw this thing on the?
You can, yeah, you can do that.
Settle back, Jason.
Nope, you're ready? Here is what I'm looking at. I am going to write something here, and you're going to shade it accordingly.
That's not it.
It looks like a cup.
I think it's just an ellipses and then it's
It's so important. Is that a cup?
Okay. Okay, hold on. F of x is 1/5 x. I want you to use a pencil, whatever it is, highlighter. What piece of this picture describes f of x equals 1/5 x over the interval from x equals 0 to 3? It is not the whole thing. You've got to know what part of this picture describes just what I wrote there. The function f of x equals 1/5 x over the interval 0 to 3. What part is that? That is where? Yes.
like that top line.
It is just this line, okay? This is the line, right? Right here. Okay. Next piece. Okay, what's that? The area bounded by f of x over the interval of x from 0 to 3 and the x-axis. So the area bounded by that line and the x-axis over the interval from 0 to 3. What would that be in the context of this picture? The whole thing, there's a piece of it. What part is that, Jason?
I don't know. It might be like half of the area of the cross section.
Okay, and maybe you're someone who wants to go over here and just do it on a separate axis if you want to. Let's see, you said 1/5 x just looks like this from 0 to 3. Here's 3. I'm asking you, where is the area bounded by f of x over the interval from 0 to 3 and the x-axis? Where would that be in this picture? Or I can do this picture first and put it on this one.
It's just like a
What shape is the area?
A triangle.
Okay, very good. Here. In this picture, we're going to do like this. Okay? All right. And the piece to the resistance is coming aquí.
Yeah.
Spanish.
Okay?
The French didn't understand.
Okay, this is the time where I need us all on board here.
Wait, so is that area? Is it the integral from 0 to 3?
Yeah.
Oh, it's just like the regular. Okay.
Okay, I need us all on board right now. I love our moments of levity, but they have to be like well placed, smartly placed. Okay, this is a mouthful on purpose. I'm going to underline some important phrases. A solid of revolution is a solid that is the result of some revolution. That phrase we're going to get very used to. What we're saying is that area from above, the green area, is revolved about the x-axis. And as that piece of triangular paper, if you will, is revolved around the x-axis, it's going to occupy a certain space, okay? That's the result of a solid of revolution. When you revolve something and it occupies a certain space in the course of its revolving, That space is called the solid of revolution. In the context of this picture, what is that? It is the what? It is the, what is this? It is a cone. It is the whole thing. Now, this is going to be very important. I'm going to do this. It is the entire cone. Okay? And what's very important, I'm going to distinguish something. Notice I said an area is revolved. I did not just say the curve was revolved. Because the area is revolved, what I have here is a solid. It's not a hollow cone. We're going to get to the distinction between revolving an area versus just a curve. If I just revolve the orange line, or my orange line, I would have a hollow cone. We're talking right now about a solid, the solid that results from the area being revolved. I am now going to pause for a second. I'm actually going to add this just so I can see, like, this is kind of the center of it, right? Okay, questions, yes?
This is a volume, right?
Beg your pardon?
It's a volume.
Yeah, it's a volume, sure, it's a volume, yeah, okay. And then what we're going to do is we're going to take this drawing and we're going to bring it down and redraw it. Yes, Nicole?
Wait, so when you're saying like the area is like revolved around the x-axis, so it's like like that triangle like filled in is like
Yes.
like 360 around the.
X-axis.
Okay.
Yes. In case you're wondering, what if we revolve around the y-axis? We are getting there. We are getting there. So what's really important, a couple of things. We're revolving an area. Okay, we're not revolving a curve. That is coming. When you revolve this area, you get a solid. All right. I am now going to write a couple of observations. This solid could be thought of as, okay, I'm going to do this a couple of times. This solid could be thought of as infinite cross-sections that are circular in shape. In other words, what am I saying? If I were to slice into this cone, I would have infinite circular cross-sections. I'm not the best visual artist, but the point is that this solid is essentially an aggregate of infinite circular cross-sections. Infinite circular cross-sections. They are stacked here, okay? And I'm going to do this. I'm going to pull one out in a second. These are infinite cross-sections. In fact, the smallest circular cross-section is right here, so to speak, okay? I'll draw a few, and I'm going to pull it out for a second, okay? One of these is called a solid circular cross-section. Solid because it's not, notice it's like the entire circle is part of the solid cone. It's a solid circular cross-section. You can say solid circular cross-section. The mathematical term for a cross-section that is circular and solid is called a disk. Okay, it's a disk cross-section. When you say disk, disk means circular, solid cross-section. Okay? And I can also, let's add this observation. The volume of the cone, here's where you have to get a little bit abstract. The volume of the cone could be thought of as the summation of how many circular cross-sections are in here, everyone? Infinite. The volume of the cone is equal to the sum of infinite circular cross-sections. Circular cross-sections is what? We'll take the what of each cross-section. If I add them all up. Yes. Yes, yes, yes. And we have been here before. We've been here before when we've talked about summing up infinite something. Pause for a second. Go ahead, Yuri. Yes.
So then, like, say for like the volume of other shapes, like volume of cylinders, it's You don't multiply the cross section by infinity. You multiply by the height.
Yes, so I will, and you know what we're gonna do, you're gonna see all those formulas like pi r squared h in a whole new light. You'll see they came from calculus. So you know pi r squared h is volume of the cylinder. We can actually prove it now using calculus. Not there yet though. Not there yet.
So is that what you look for?
Yes, yes, all, yes,
Oh,
yes,
sorry.
yes,
So
yes, yes,
Oh.
yes.
Google's giving it to me.
Okay, all right. Now, here is the thing. If a volume of a cone is a sum of infinite circular cross-sectional areas, you know, whenever you hear sum of infinite something, you know you're gonna have what symbol propping up at something?
Sigma.
A limit of a Riemann sum, or you're gonna have what?
An
integral. Okay, I mean, by definition, the integral literally means it comes from this idea of adding up infinite things. The story continues. I'm out of room, but that visual, we need it. Notice something here. And by the way, just so we're clear, this is the x-axis, this is the y-axis, not written on your paper, but should be understood. Are my circular cross-section areas, are they stacked? Stacked. Stacked, right? Are they stacked over an interval of x or over an interval of y? The cross sections are stacked over an interval of x. That's going to be very, 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 very important. Very important. Okay, everyone. The area of a cross section equals, okay, area of a cross section. In general, what is the area of a fill-in circle?
Pi r squared.
Pi r squared.
So it's like 5x.
Well, let's see. Hold on a minute. Let me go over my drawing. Look over here. Ready? When you figure out, because the issue here is what's the radius. It's like the critical body part of each cross section. Always draw the critical body part to the original curve. Not its image, the orange line. I'm going to go over here. Do you see the radius is right here?
Yes.
The radius is right here, everyone?
Yeah.
Okay, ladies and gentlemen, someone please give me what describes this distance?
Oh.
1/5.
F of x. This right here is y equals 1/5 x. Yes. Do you understand?
Wait.
This vertical distance is the distance from the x-axis up to the curve. This distance here is y equals 1/5 x. We're drawing it up to the original curve. Does everyone see that? I can't rush
Wait.
this. Do we
Oh
see
wait,
the
because
history?
is that the line? Like the if you just look at the top, like the orange line
Yeah,
of the
the
cone.
orange line was this, Nicole.
Oh, so that's the 1/5 x.
Correct.
Oh, okay.
Everyone okay? Let's walk over here. So the area of a cross section is, take a look, pi times 1/5 x squared. Okay? That is the area of each cross section because obviously the radius depends on where you are in this solid. Okay, here we go. The volume of the cone. We are ready. The volume of a cone is a summation of infinite areas of these circular cross sections, and they are stacked over an interval of x. So first tell me, I'm adding up infinite, here we go, look at me, adding up infinite something. I'm adding up infinite circular cross sections, okay? Tell me what the interval of my addition is going to be. What is the interval over which my cross sections are stacked from where to where?
0 to 3.
0 to 3. If this is x, and if this is x, what is my dummy? Okay, it's gonna wait in the wings. Waiting in the wings. This integrand here is going to be the thing that I'm adding infinite of. So this integrand is going to be the what?
The area of the surface. Yeah.
I'm going to pull pi through automatically. whatever is a constant I can pull through, let's take it right out. 1/5 x squared. Okay? This is it. That makes sense, that rollout, that very slow rollout. Everyone okay with that?
Yeah.
All right. Pause for a second. Jason.
Are you sure that the limit of summation is
So the first thing I wrote down before. So if you go very, very far back to when we first did the limit of a right endpoint Riemann sum, all those long way through, though, but we found that actually equals the definite integral. Like that's the limit of Riemann sum equals the definite integral by definition. But we also saw that we worked the long way. We did the long, arduous limit of a Riemann sum, and you love them. Not at all.
Disagree.
Okay. Does that answer your question?
Yeah, but the summand of the Riemann sum is different from the integrand of.
They're actually the same if you let yourself just play with the idea. Like the summand of the limit of Riemann sum is actually the integrand, but only the summand, it's not approaching delta x is approaching 0. So they're not identical. But did you see, so I already erased it, but did you see how the height and the width are in the integrand?
Yeah.
We can talk more. You need a clean piece of paper. Please sketch me this curve. Cobble and axes together. Sketch me the curve, please. Y equals x squared, only between 0 and 2. I want y equals x squared, only between 0 and 2. Yes, Nicole?
Well, you're saying that like the dx is like the height. So in the volume
it's
of
like the width.
the width. So like in the volume of the cone, how is it like the?
So it's like, because each of these, what happens is they each have a thickness.
Yeah.
Like they're pennies, but even a penny has a thickness.
Mm-hmm.
But we're saying that this width is approaching 0. So these little discs.
Oh, so that's how you have infinite.
Yes.
Oh, okay.
Yes.
Okay.
Yes.
Gotcha.
Yes. All these questions are such fantastic ideas.
Wait, what was this?
I want the graph of y equals x squared only between 0 and 2. Was that what's better?
No, it's like.
I mean, this is certainly also an idea that takes a little bit of gelling. Everyone okay? Okay. I would like you to now shade the area between what you just sketched and the y-axis. Okay. Probably can see where I'm going. Then I'm going to ask you're going to see this symbol a lot, everyone. When you see this symbol, it's like a curved arrow over an axis. What they're asking you to do is revolve about that axis, okay? Take this region that you just shaded, revolve it around the y-axis, and then with your best artistic ability, draw the solid that is occupied. Okay, to the best of your ability, it may be easier for you to describe the solid. Okay, if I take that area and revolve around the y-axis, there's a solid of space being occupied. What does that look like? Upside down Hershey kiss? No, it doesn't like. What does it look like?
Yeah, like a
Bowl
Yeah.
filled in,
bowl.
right?
Take a whole soup.
So like half of a.
Of the sphere.
Half a sphere. It's not half
Like a
sphere,
sink.
though.
Like a sink.
Like more.
A what?
Sharp.
Sink.
A sink? A sink.
On the wall.
Solid. That has no basin. Fair enough. Okay, fine.
So
I'll
a
leave
chunk
you
of
there.
marble. No.
This is a solid. Disk cross sections. Here is a solid that has disk cross section. If you're asking me, will we ever do cross sections that are not disks? The answer is yes. Not yet. A disk again is a solid circular cross section. Tell me how the disk cross sections are stacked in this world. They are how?
Vertically.
They are stacked vertically over an interval of what?
0 to 4.
Which is an interval of what?
Y.
It's an interval of y. I'll draw a few circular cross sections. I'm also going to draw the critical body part, which is the radius. We're going to draw it to the original function, never to its image. Draw the body part to the original function, which means I'm going to draw a few here. These are my cross sections. My cross sections. Why don't mine look so nice? Wow, I'm so upset. Okay, my cross sections. My cross sections. Here is my radius. I'm going from here I am. Here I am. Interesting. My radius now is an x distance. I wonder what that x distance would be. What is that x distance? Back in the day, my radius was a vertical y distance. What is my radius here? That's an x distance. It's a varying x distance. Yes. This is x equals root y. The radius here, this radius equals root of y. Okay, all right, let me see you put together, please, an integral expression that would describe the solid of this revolution. Integral expression, watch your dummy, watch your interval, watch your integrand. Your question?
I just like, I think it's kind of like the case task, but how do you know that the sum of the circular cross section there is equal to the integral of its answer?
Oh, I know. So the part that I'm obviously skipping in this second go around, I'm skipping kind of like doing the Riemann sum longhand. Check what happens.
Wait, how is this like a Riemann sum though? It's like a the integral. Yeah, but you're not doing a breadth. You're not just finding the area under a curve, are you?
You're not, but you're finding the area of something that's getting infinitesimally squeezed, so to speak.
You think about, like, you just accept the integral, like the regular thing that we just been doing is what it is. Yeah. Then, if you think about that, then all you're doing is like the formula for a circle. But the radius is now the function. So it's just the formula of a circle with the function, whatever it is, plugged in as the radius.
Miss Yam, is the solid of revolution the same thing as the volume, or no?
The solid revolution is the actual thing, finding
It's
its
just pi
volume.
r squared.
Oh,
Like
okay.
the solid is like what
Is
results.
whatever.
But I understand what you're saying. I think you're asking for like a more robust connection.
Like I get like the I get the concept.
Yeah,
it's
yeah,
the-
yeah.
Why is it not sigma? Why
I
is it?
know. So I kind of skipped that step. I'll do it longhand. I'll do like an optional screencast so you can see the parallel work in the sigma.
But I
Last
went
time.
through my, oh yeah,
Yeah.
that's like Romano's.
I want it. Let's see who can give it to me. Everything. Jabril, you. You got it. You got this. Go, Jabril, go.
Yeah.
Come on.
Or,
The integral from 0 to 4.
oh wait, put a pi.
Put a pi in
Forgot
front.
the pi. Wait, you're a squared. Yeah.
Root y, all of it squared. dy.
Oh, you have to square it because it's like
Yeah, it's the
area.
radius squared, pi r squared. So here's the thing, and as you can see, yes, Cameron.
So that gives us the space in the. So if we were thinking of it as like a sink, that gives us the space that's not the solid sink, but what's the?
No, here in this is why zinc was not a great analogy. This volume is the actual volume of the solid material of this solid thing.
Or what if the solid material be?
It's the whole thing. There's no hollow part. Like this thing that results is a solid thing.
Like it's all filled in.
It's all filled in.
Oh, it's all filled in.
Yeah, because Cameron, look, what we shaded was a region. You
It's not
understand?
like hollow in the middle.
It's not like this is what I said. We didn't revolve a curve. That would be hollow. We revolved a region. This whole thing is all filled in. Very, very, very good. All right. I would say, oh, what a great, fantastic class. You all get that? Like, get the.
I'll get there.
Oh, yes.
Oh, nothing. I'm just gonna stop the screen.
Yes.
Well, if you don't,